Our speaker tonight is RTB research scholar, Dr. Jeff Zweerink. He has a PhD from Iowa State University and is an astrophysicist specializing in high-energy astrophysics. He's a part-time project scientist at UCLA who apparently stayed up all night last night working on a project, so he's a little tired today, we understand. He writes and speaks frequently on this topic of exoplanet research. Please join me in welcoming Jeff to our meeting tonight. Welcome, Jeff.
Well, thank you. I appreciate the opportunity to be here. And I have to say, this is one of the funner or more fun. I always like to say that wrongly just because typically somebody gets irritated at that. My father-in-law was an English professor and my wife doesn't like it when I say that wrongly, but it was just a fun talk to get ready for because it gave me an excuse to go in and start looking at what the James Webb Telescope has actually done, what it's found. You know, I've seen some of the images and done a little bit of work, so it's not entirely new, but this is just a pretty cool telescope. And if I'm honest, it's kind of funny because this is one of those telescopes I was never entirely sure they were actually going to launch because it was always about 5 years until it was supposed to be launched. And then a few years ago, or just recently they did. And from a technological standpoint, it is just a marvel to look at. And so what I wanted to do today is just to share some of the things that I have found that I find fascinating. There's going to be a fair bit of just some of the science that they've done, what they've been able to look at, how the telescope works. I'm actually not going to spend a lot of time on apologetics so much and say, oh, here's the latest thing that it's shown, but more kind of just open up the floor saying, hey, here's what it's done. Here's what it's capable of. Here's what to look out for. And then just kind of have some discussion of, I think anytime we build an instrument that allows us to study God's creation better, you find lots of things out and find more evidence, things that help us know and understand God better. So as I've been looking at the latest from the James Webb Space Telescope, one of the things that I found that was just fascinating is that it has a lot of cool things. This was an image I ran across, and honestly, when I first looked at it, this had kind of a Lord of the Rings. My immediate thought when I saw it, it's like, oh, this is like one of those galloping horses. The horses that turn into, or the water that turns into horses and gallop away. Just kind of this fascinating picture. I showed it to one of my kids and they said, oh, that kind of looks like Marvel. I can see Tony Stark. I can see Thor in there. I can see Iron Man. But this is an actual image from the James Webb Telescope. And kind of describe a little bit in detail what it is in a bit. But just kind of as I was looking at what the James Webb Space Telescope has done, there are just some pretty startling and remarkable images out there. And so I thought I'd just kind of start by showing some of those. This is actually the Eagle Nebula. And there's a bunch of contrast between what the Webb shows compared to Hubble. But again, one of the more iconic images that are out there. This one, I was just kind of flabbergasted by this. This is a galaxy, I believe it's M74 or M47. And it is otherwise known as the Phantom Galaxy. And I first saw that and it's like, wow, that is just bizarre. It almost looks like there's an aspect to where as I'm looking at a lot of these James Webb images, it's kind of like you're looking at a ghost or looking at something that's not quite there. It's just so different from what I'm used to seeing from telescopes, especially telescopes that provide images. Just the clarity, the resolution, the detail of what's in there, the contrast in terms of the light and the dark, the colors. There's a little bit of caution I'll throw into that in a few minutes here. But again, it's just finding fascinating images, things that we really have never seen before. This is another one. Normally, I'd kind of throw it out there, and if anybody wants to chime in on this, I'm curious what you actually think this object is, because this is an actual image. It's not somebody that sat down and drew up something with their power or with their Adobe Photoshop or anything. This is an actual image. It looks like maybe we've got some people there in the chat that are weighing in. Very good. Actually, somebody does know. One of those, Ben, where you give the right answer right away. That's no fun. But yeah, Ben is actually correct. This is Neptune. And yeah, you normally look at that and you see, oh, rings, you're thinking Saturn, possibly Jupiter. And it turns out Uranus, all four of the gas giants have rings around them. But again, there's just kind of this otherworldly look to what's out there. Saw it in our RTV post. I like that, Ben. Very good, very good. But again, there's just this kind of otherworldly look to what the James Webb Telescope is showing us out there, and the clarity and the detail. What I thought was pretty impressive about this was I saw an image that had the Hubble Space Telescope, it had the James Webb Telescope, and then it had a picture from Voyager. And in all honesty, the James Webb Telescope was about as clear and in resolution as the image was from Voyager, which when you think about it is spectacular, because Voyager is taking that picture from pretty much up close right there next to the planet, whereas James Webb is taking it from millions of miles away, and yet it's still able to see basically that level of clarity and detail to it. So again, it's just one of those things that I found very remarkable. This is an instrument really unlike anything we've ever launched before, anyone we've ever developed, just in terms of what it does to advance our ability to see things. It is unrivaled in its clarity and its presence. It's what it can show us and how well it works. And part of that is just due to how it was designed. This was another image, again, that I found incredibly fascinating, because this is actually two stars. One of them is a giant O star that is, if you go from least massive to most massive stars that are hydrogen burning stars, M is going to be M and K stars are going to be down on the least massive or the lightest stars. And you go all the way up to O are some of the most massive stars. And this O star is orbiting around what's called a Wolf-Rayet star. And as it does, these things orbit around, and about every 8 years, they get close together. And when they get close together, it ejects a shell of material, and these shells are just moving out. And as they're moving out, the light from the stars is illuminating them. And you can see these concentric rings that are going out. And again, I could imagine somebody drawing that, but the fact this actually exists out in space, I just thought was pretty remarkable, of the sorts of things it's finding. And again, it just shows the level of detail, the level of clarity and resolution that the James Webb Telescope has. And so, like I said, these are shells of dust that are formed, and you can go find all of these. I would encourage you to just go to the James Webb Space Telescope website. I think it's called Webb Telescope. But it's easy to find, and there's a whole catalog of stars, galaxies, nebulae, planets. It's found various things that you can go and just kind of read about all the details. It is a pretty remarkable thing what we've been able to find. I was just looking to see if I could actually find. I have written down where what the instrument is. Yeah, it's called esaweb.org, has all the images from the Hubble or from the Webb telescope, and all the stuff that I'm doing ultimately gets traced back to there, although I'm adding some more details in that I've found as I've been investigating them. So it's and one of the cool things I found, and I just thought I would throw this up because this is that galaxy, it's NGC 720 or 628 Phantom Galaxy, also known as, pretty sure it's M47, that you can actually go download data from the Webb telescope, get some analysis software that's publicly available, and start putting together images like that yourself. Because this image here was actually put together by a citizen scientist, nobody who has any formal scientific training, but has just learned how to get access to the data, to download the software, to download the images. I point out this particular article because I forget the exact, I want to say it was in Science Science Alert. It's one of those kinds of magazines, but they actually just give you kind of a step-by-step of how to go to find the image or find the data on an archive, a publicly accessible archive, how to filter it, how to get the actual data, how to get the software that allows you to start looking at things, and how to put it all together and make these images. So if you have any artistic sense or just kind of interested in how to do all that, I thought this was a pretty cool thing, that this is, because it's a NASA instrument, this is publicly accessible. Most of the data is, and at some point, all of the data will be available. So kind of, like I said, pretty remarkable the sorts of images you can make. And it isn't something you just have to be a university level or, kind of a professional scientist to be able to get access to the data and make some of the images. This gal has been doing this for a number of years, so she's gotten good at it, but you can go out and display and make some of these images yourself. And she that article walks you through how to do those sorts of things. And so one of the questions that I had as the Webb started, James Webb Space Telescope, I'm just going to call it the Webb because it's easier. As Webb started bringing back images, like, how does this compare to the Hubble Space Telescope? Because these were the sorts of things that happened when the Hubble started operating, that even in its uncorrected state, the Hubble Space Telescope was by far the best optical telescope we had. And one of the, as it was getting fixed, what started out being good images became phenomenal images. And it's just transformed the way we think and what people think about when they see imagery. In fact, I remember being up in Yellowstone. The Hubble Space Telescope had been putting images out, and there was an opportunity. The Amateur Astronomy Club had set up a bunch of telescopes, and you could look at Jupiter. There were some globular clusters. There were just various things you could look at. And I remember Saturn was up. I do remember that. And I remember going out there, and I was with my family, and my parents were there, and thinking, is this going to be that interesting? Because if you're used to seeing telescopes or images from the Hubble Space Telescope, and you now go look through even a 20-inch telescope they just don't compare. I mean, that's how good of a telescope the Hubble Space Telescope was. And we ended up having a great time enjoying seeing a lot of things out there. But one of the big differences between the Hubble and James Webb is that if you look at the electromagnetic spectrum that it covers, you got the gamma rays, which are really high energy light off to the left there. You got radio waves, which are very low energy light. The biggest, or the way to distinguish that, you can talk about it in terms of energy, you can talk about it in terms of wavelength. For radio, you got very large wavelengths, anything from meters up to tens and even thousands of meters. Whereas you go down to visible, infrared, ultraviolet, that's in the visible is 400 to 700 nanometers, which is 400 to 700 billionths of a meter. And then you go all the way down into gamma rays, and nobody talks about gamma rays in terms of energy or wavelength. It's always in terms of energy. But if you get down there and you're looking at the gamma rays, even up at Swift and RXTE, my background is actually in gamma ray astronomy, and the gamma rays we were looking for were even off to the left end of this, or even off the left end of this chart. But what you'll notice is that the Hubble Space Telescope and the James Webb Space Telescope, they do not cover the same range of wavelengths. Hubble was primarily visible and ultraviolet, although it could see a little bit into the infrared. James Webb is primarily infrared, although it can see a little bit into the visible. And so it's important to keep in mind, and I think that's part of why so many of these images appear kind of ghostly and otherworldly. It's like, these are things we don't see because the way they're being portrayed is though they're actual photographs, and they are actual data that have been transformed into images. But these are images that we will never see because we do not see in infrared light. We see invisible light. And so I think that's something important to remember, especially, so here's a photograph or an image from the Hubble Space Telescope of the Carina Nebula. And you can see there's this, it's called the cliffs. You've got the what looks like this nice boundary between, there's the nebula and it's emitting gas off into this other region, and there's light being, or light, ultraviolet lights being pounded down into there, and these are largely a pretty close to actual color of what it is. And so here, this is the Hubble version of that image. And I went out and found, it turns out they took with the Webb, they took a similar sort of image. And what you'll notice is that you can see a lot of the similarities there. You see you've got this little nodule that's sticking out there. There's a valley kind of walking across there. One of the things that immediately stands out, though, is that if you look at the stars in the background, you'll notice that there are a lot more stars in the James Webb image compared to the Hubble image. And that's driven by the fact that Hubble sees things in visible light, James Webb sees things in infrared light. Infrared light will penetrate through the dust more, whereas the Hubble will see the light reflected off the dust, and that's as far as it can see. The Webb will see through the dust and see the stars that are in the background. Now, these are not very far into the background. It's not like we're looking across deep out into space, but you can see there's a lot more stars in this region. You can see a lot more stars in the Webb than you can in the Hubble. My inclination, or when I first saw that, I thought, wow, look at it, took the resolution that Hubble had, it just greatly amplified the resolution, and we see things better. What's important to remember in here, though, is that all of the data from the Webb, which is down there on the bottom, the highest in wavelength it sees, the shortest wavelength it sees, is actually red. So all the stuff that is blue is actually red in its field of view. So this isn't an actual image. It's not a photograph the way we would look at a photograph. It is data from infrared that is now transformed into visible wavelengths so that we can see it, but it's not a picture you could actually see unless you saw an infrared light. And we don't see that. So always bear that distinction in mind. So none of the colors you're going to see in the James Webb images, they don't line up with what we would see if we were looking. They've all been transformed into something else. And so just bear that in mind as you're seeing things. One other thing that stood out to me in this image is if you notice the stars, so we can go up here and look at this star in the Hubble image, and you notice it's got this kind of crosshatch pattern on it. It's these perpendicular sets of lines. You go down and you look at the Webb, and there's actually, it's a hexagonal pattern, and there's actually this smaller crosses on there. And I'll kind of explain why those all show up that way in a little bit. But it's actually a great way to tell whether you're looking at a star or not in either the Hubble's, especially in the deeper fields, the Hubble deep field or the deep images given by the James Webb, is because any sort of point source, which a star will be when you're looking out into a deep field image, all of them are going to have these little crosshatch patterns on them. It's a great way to identify stars in an image. So in like the Hubble ultra deep field or the James Webb, what's been called the James Webb deep field, somebody ever asks you how many stars there are, and you don't see a lot of crosshatches, there are not too many stars in there. But again, just remarkable, the level of detail. The field of view for the Webb is actually larger than the Hubble was. And so I had to shrink this down and crop it quite a bit so that the Hubble and the Webb align. But again, you just see the level of detail, the level of precision, and the resolution that the James Webb has is pretty remarkable. And a lot of that is, what drives a lot of that is that it's looking at these different wavelengths that allows it to see things, see through the dust where the Hubble was obscured by the dust. This is another one, if I remember correctly. This is a galaxy that is called IC 2553. And what you have here is the Hubble image on the right and the Webb image on the left. And you can just, again, what this highlights is that they're looking at two different wavelengths. And by looking at these two different wavebands, you see a very different components of what's in this galaxy. This is one of these grand spiral galaxies, where you, or grand design galaxies where you see the spiral arms. If you look closely, I mean, you can go actually look on the website and you see that this star is right in there. And so these are very clearly the same object, but you kind of see this, what you expect a galaxy to look like in the visible, and this kind of ghostly, ethereal apparition on the left. And again, I've emphasized that mainly because I want you to walk away and remember, when you're looking at Webb images, just remember they're not actually photographs like we're saying, whereas the Hubble, those are actually pretty close to what you would see in a photograph. This was one of my favorite ones, and this is again the one processed by that citizen scientist. And again, it's referred to as the Phantom Galaxy. You can kind of see why. You've got this, you can see down into the heart of the center of the galaxy where you can see those older blue star, those younger blue stars. You can see kind of red stars out there. You see just a whole lot of stuff. And I've actually looked at this with both the Webb and the Hubble, again, optical and infrared there. And if you look on the left, you can see from the Hubble in the center, you've got these kind of orange yellow stars, whereas you got the bluer stars, the newer formed ones are out on the edge. Whereas with the Webb, you're seeing down into that stuff, you're seeing things that are, the red is characterized as blue. So again, those are not newer stars. The newer stars are out here in the blue because that's actual physical image. And why I highlight this is that by looking at things with both the Hubble and the Webb, you get this center image, which actually gives you a whole lot more detail of what's going on. And one of the great tools that the Webb will bring is that it allows us to look at a lot of different, or to look in different wavelengths so that we get a lot more information as to what's going on instead of just having one image. And so now we've got these two premier telescopes that allow us to do that. And here's the Eagle Nebula. Again, I've talked a lot about how different they appear. Notice that, again, the stars that are in the background of this are not off in deep space. They're still all in our galaxy. The Webb cannot see through the interstellar medium very far, but the Hubble can't see through the dust. So where the dust sees, or the Hubble sees all the dust, Webb looks through the dust and sees the background, but sees all the stars in the interstellar medium. And again, this is a region, it's about 6,500 light years away, about 1/4 of the way towards the center of our galaxy, about 8 light years across. But this image in the Webb is actually about 156 megabytes. And you can just zoom in. And what you see is that there are just stars that are forming all through this region. The Webb allows you to get in and actually see the stars that are being formed, the stars that are breaking through on the edge, and an unprecedented level of detail of what's going on in this incredible star forming region. So there's another big difference. Because James Webb works in the infrared, it needs to stay a lot cooler. And if you compare where the Hubble is, you'll notice that the Hubble is orbiting, 500, 600 kilometers above the surface of the Earth. Moon's about 400,000 kilometers. The James Webb is out at 1.5 million kilometers away from the Earth, and it's at a particular point. It's at this L2 Lagrange point. And why it's there is that in its orbit, it's kind of like a kind of the equivalent of a geostationary orbit. It's always going to be, if the sun's here and the Earth is here, the L2 point is always going to be out here. So as it orbits around, as the Earth would move up here, the Webb would move up and be up here. So one, the Earth is kind of blocking some of the light from the sun, but more importantly, it's at a place where it can stable, and it'll just orbit around that point and it won't drift off into space. So it's a stable place that's very far away from the Earth. The Earth is actually pretty hot. It would heat up all of the instruments on the Webb. And so by putting it 1.5 million kilometers away, it's able to keep it cool. It has a sun shield around it that is about the size of a tennis court, but that sun shield blocks all the light, radiates it back away from the telescope, and it allows the telescope to remain cool so that all of the infrared instruments work well. Because again, if you're going to look at infrared light, or things that give off infrared light, that's a way of measuring the amount of heat. So if you go take an infrared camera, humans just light up very brightly. because they're giving off quite a bit of heat because we're at 100 degrees Celsius. Or sorry, 37 degrees Celsius. Water boils at 100 degrees Celsius. And so part of the reason why, one of the big differences that allows the James Webb to do this is it's located so far away from Earth. That allows it to stay cooler, and it allows it to get a lot more to see that infrared light. And this is one of those, again, just shows what you can see by looking at things with the Webb as opposed to other instruments. And this is two different wave bands, two different infrared wave bands of the Cartwheel galaxy. And this was a galaxy that I actually got to do a little bit of studying on when I was an undergraduate. Two of my one of the astronomers that I was working for when I was took classes from at Iowa State was doing galaxy dynamics and trying to figure out how do galaxies form the way they do. And particularly this galaxy, we were doing simulations that showed if you have a large disk galaxy and a smaller galaxy kind of off to the right there that has passed through it, it will cause this shock wave. And as that shock wave propagates out, it causes a lot of star formation. And so you see a lot of the gas and dust there, the red colors. You get out into the ring, you see things get a little bit bluer. That's even more red. And if we now kind of shift it over, we can look at when you look out in the mid infrared, that doesn't see any of the stars that are forming. It sees a different stuff. And now you can go add on what you see in the visible region. And so this is a Hubble Space Telescope image. You can see that these different wave bands allow you to see different parts. It's kind of like being able to take an X-ray. You take a visible, so you get to see the surface. You take an X-ray, you get to see inside, and it just allows you to get a lot more detail of what's going on. And you can see just the intense star forming that's going out in this very blue region, because in optical images, blue regions are recently formed stars that are very bright. Red regions are stars that have formed long ago and have cooled off. And so, these are the sorts of things that when you're taking the infrared and moving it into the visible, you got to remember that what you're seeing doesn't always line up there. So this is probably the dominant reason why the James Webb is able to add so much more resolution, is you just look at the differences in the mirror size. So for the Hubble primary there, you got about 2.4 meteor radius. So it has a surface area, or a coverage area or surface area of about 4 meters squared. You contrast that with the James Webb, it's 6.5 meters radius, which gives it about 25 meters squared. And I will just warn you, you can do those calculations and you'll find that's not quite right. You also have to take into account how much does the secondary obscure and things like that. But when you do all the calculations, you'll find that the James Webb is a little bit over 6 times the size, which means it can collect 6 times the amount of light, which allows it to see things. You get better resolution going from 2.4 to 6.5 meter radius. But so not only do you get better resolution, you get better light collection area. And you'll notice that hexagonal pattern on the James Webb, where for the Hubble primary, it's circular. It's this hexagonal structure that actually causes that 6 spike structure on the stars that you're seeing, because every time you got a surface, you end up getting diffraction patterns around it. And so that's why you get those 3 lines spaced at 60 degrees around the stars. And then you also get some of that from the supports designed there. You get 4 or 5 from that, but they line them up so that most of the ones on the supports line up with the ones from the primary mirror. But really, the difference in mirror size allows you to just see things with better resolution and much, much farther away. And so this is why the James Webb was built, because if you look at the Hubble Ultra Deep, or the Hubble Space Telescope, or the Chandra Telescope, which is an X-ray telescope, and you ask the question, how far away or how far back in time they can see, you can see that they can get back to when the universe was about 1 billion years old. So between 11, 12, maybe 13 billion years. The James Webb was designed to get all the way back to where the first stars and the first galaxies were formed. In fact, see through when the first galaxies were formed to get all the way back to where we can actually see the first stars. And if you're going to do that, you got to realize that as you look further away, things are redshifted. So instead of looking in the visible, you need to move into the infrared. Well, if you're going to look in the infrared, you've got to get colder. And if you're going to look in the infrared, to see further away, you just need more light collection power. And so all those things contribute to the way the Webb telescope was made. And just from a technological perspective, what the James Webb did was remarkable, because it was launched on a rocket, launched out into space. It's got to travel all the way to where it's to this Lagrange point, which is further away from the Earth than the moon is from the Earth. And then either on its way or when it gets there, it has to take all of these components and unfold them so that you have mirrors positioned at the nanoscale level or at the nanometer level, so that it can actually see this infrared light without getting distortions from the mirrors. And all of these mirror segments are actively controlled. It's a technological just wonder, if you will. And I'm just pretty impressed with not only what we're finding, but that NASA and all the groups involved were able to make this work. But this is what it was designed to do, so that it can go back and find those first galaxies and first stars. And so as it's gone out to do this, one of the other things, because it's got such good light gathering power and such good resolution, it can actually do better finding of exoplanets. And so it's already found some exoplanets. Two of them here, this WASP 39b, WASP 96b, were found using the transit technique. And there, what happens is you've got a star with a planet orbiting around it, and the geometry is such that occasionally this planet passes in front of the face of the star, which occults the light and allows us to see that dip in light. And you can see the dips in light here. What was cool about this is on WASP 93 or 39b, they've got different wavelengths that it can monitor it. They're different infrared wavelengths, and different wavelengths were absorbed different amounts. And so what they were able to do from that, and also by looking at the light as it's going through the light going through the planet and blocked by the atmosphere, they were able to take that and now ask the question, can we detect any particular compounds in the atmospheres? And for 39b, they found this signature of carbon dioxide. And for 93b, they found all these signatures of water. Now, lest you think we're on the verge of finding a habitable planet, both of these are gas giant planets that orbit, around their stars in about 3 or 4 days. These are intensely hot planets that are not anywhere remotely close to being habitable. But again, what it shows is the capacity that the James Webb Telescope has. This telescope has the capacity, as I will show here in just a second. Not only can it detect planets by the transit, but can also detect direct light from the exoplanet. And here, what it will do is it actually will occult the light, put a block up in front of the light from the star, and then look for light from objects surrounding it. And this particular object, from the Hipparcos catalog 65426, they were able to block out the light from the star in 4 different wave bands. You see, you go from, these are just the names given to them. You go from the near infrared out to the mid infrared, and you can see the light from the planet in 4 of the different filters. And so this is a 6 to 8 Jupiter mass planet that's about 115 to 220 million years old, which is contrasted with the planets in our solar system, which are 4.5 billion years old. And this one orbits out at about 100 astronomical units, as opposed to Earth, which is at 1 astronomical unit, and Jupiter, which is about 5 astronomical units. But based on this object that we knew there was a planet, so they went and found it with the Webb, they were able to calculate and say that there's potential to see Earth-like planets orbiting around sun-like stars in Earth-like orbits, and so being able to see Jupiters and Saturns and maybe even Neptunes and Uranuses, and potentially being able to see, an Earth-like planet around very close stars. And so this is pretty exciting what the James Webb will be able to do in terms of finding planets over the next 20 years of operation. But like I said, the James Webb was built to look out deep into space, and this is kind of the deep field of the James Webb. Again, notice the stars there. They've got that hexagonal grid or hexagonal flare pattern on them. This was an image that if you take the Hubble ultra deep or the Hubble deep field and ultra deep field, those are about 1/50th the size of the moon on the sky. This is if you take a grain of sand and hold it out at arm's length, this is about the size of the region of the sky there. Now, just for scale, if you take your thumb at arm's length, that's about the size of the moon. So the Hubble was 1/50th the size of your thumb. This is a grain of sand. And so this is a smaller region, but again, just a wealth of galaxies and stars in here. And you'll notice that a lot of these objects are kind of elongated. It looks like somebody smeared them out. That's not actually an artifact. That's this cluster of galaxies is lensing more distant galaxies in the background. And that's allowed astronomers to go and date galaxies back to 400 million years after the Big Bang, maybe even some as far back as 250 million years. And we might be able to push that even further, depending on how luckily, or how things are aligned in some of the other clusters that they're going to look at. What's remarkable, again, just from a technology perspective, is as fascinating and as amazing as the Hubble Ultra Deep Field was, it took almost 12 days of observing. This took 12 hours of observing. So again, it just gives you a scale of how much improved the James Webb is compared to Hubble. But again, just recognizing they're really complementary telescopes. They don't quite do the same thing. As astronomers have been looking at these, what they did notice, though, is that these galaxies, they're finding these galaxies that are more massive and more complex than expected. More massive is odd because galaxies, we expect them to be small and grow over time. And so we found galaxies that were more massive than what we expected them to be. And we found Milky Way type galaxies where you've got these disk structures and more advanced, again, more complex structure in them. And both of these were surprising because we expected, again, these earlier galaxies to be much smaller and kind of in a region, or the general idea is that you're going to see a whole lot of interacting galaxies. It's going to be a lot of hodgepodge, a lot of odd shapes. And what we're finding is there's a lot more complexity and mass in there than we thought. And this generated a lot of press because there was a scientist who said, hey, the James Webb is showing that the Big Bang is wrong because these galaxies that shouldn't exist, they're finding these galaxies. And this fellow, his name was Eric Lerner, claimed not only to say, okay, this is the Big Bang wrong, what the Big Bang is predicting for the way galaxies look, the James Webb is saying they don't look that way. And in his model, galaxies form via a different mechanism, and you expect them to grow more rapidly, to grow more complex structure more rapidly, and to grow larger. And he's saying not only does the Big Bang or the James Webb not show what the Big Bang predicts, it does show what my model predicts. And so he got a lot of press, largely because he had some things that were published in a conference. And so people were talking a lot about this. And so I spent some time kind of digging into what all was going on here and just asking the question, does the James Webb Space Telescope show that the Big Bang is wrong? My short answer is no. Let me give you a little bit more of the details. So when we're looking at Big Bang cosmology, the dominant driver, the dominant evidence in support of Big Bang cosmology is that we live in an expanding universe. That as we look farther away, we see more distant galaxies are moving away from us faster. This was actually the original data that Hubble used in his first publication about this. And what you can see is that as you move farther away, galaxies are moving away from us faster. Now, just for scale, the Andromeda galaxy is just under a megaparsec away from us. So this is very much stuff in our local cluster of galaxies, but we've been able to extend this not from 1 or 2 megaparsecs, but out to 3, 4, 500 megaparsecs. And we see that, lo and behold, this trend holds, that the farther away a galaxy is, the faster it's moving away from us. And not only that, we've been able to go out even much farther than that, looking billions of galaxies that the light has been traveling to us for billions of years. And we find that, lo and behold, the farther away a galaxy is, the faster it's moving away from us. In fact, we've been able to measure that relationship so precisely, we can get information on whether there's dark matter and dark energy and how much there is just based on these measurements. And for scale, if you want to look here at Z of 0.1, which is right here, we've been able to make a bunch of measurements out beyond that. And so you can see we've really mapped out a lot of the cosmos, and we find that our universe is such that the farther away something is, the faster it's moving away from us. Now, I will say this, that in Eric Lerner's model, which he says undermines the Big Bang, he has no explanation for why something that is further away moves away from us faster. Whereas in Big Bang cosmology, that's just a natural consequence of things that are expanding. If things expand, that's the way it works. The other big piece of evidence in favor of Big Bang cosmology is the cosmic microwave background radiation. And again, Lerner's model doesn't have a good explanation for why the cosmic microwave background radiation exists, but we can look at this background radiation. It's very homogeneous. We can measure its temperature, and its temperature changes over time. We can find the ripples that grow into galaxies, stars, planets, and clusters of galaxies. There's just this incredibly coherent picture. So it flows from the galaxy redshift, or the distance redshift relation, and the cosmic microwave background radiation. Those are the strongest pieces of evidence for Big Bang cosmology. James Webb doesn't weigh in on any of that. And so there's no way that the James Webb is showing that Big Bang cosmology is wrong, because it doesn't even impact the strongest evidence for Big Bang cosmology. So what do we do with Lerner's claim? Well, I'll just point you, I'm going to kind of briefly summarize what I found, but the short answer is that this cosmology that Eric Lerner is proposing has been around for decades. In fact, I remember hearing back when I was in graduate school, or shortly thereafter is where it came out, and astronomers had talked about and dealt with, addressed those claims 20, 30 years ago. And the big difference, but what Eric Lerner's cosmology is claiming, he's got a background in plasma physics, and he is claiming that rather than gravity driving the dynamics of the universe, which is what general relativity says, electromagnetic forces drive the dynamics of the universe. And in that instance, you've got plasmas that are going to drive galaxy growth. And so galaxies will grow faster and grow more complex more quickly. But electromagnetism is much, much stronger than gravity is. And so if electromagnetism is driving the dynamics of the universe, it's going to behave very, very differently. And so he had been arguing this, and there were predictions of what this plasma cosmology would show, and people have gone out and looked, and they don't line up. And so there was an article by one of my colleagues over at UCLA that was published back in the 90s. It was updated in 2003, looking at a lot of claims of what Lerner would say about how to explain the cosmic microwave background radiation, looking at the distance relationships and all of these things, and shows that they just don't line up with what the data says. And even though it was last updated in 2003, those challenges are still, or that commentary and analysis addressing Lerner's claims is still valid today. Part of one of the things that motivated Lerner to develop this was, we've got this dark matter, Big Bang has this dark matter stuff in there, and he thought that was an ad hoc add-in, that the cosmic microwave background radiation didn't have the structure that allowed galaxies and clusters of galaxies to form. That was actually one of the primary drivers of why he developed his theory. And I could say that in the last 30 or 40 years, or 20 to 30 years since, astronomers have spent a lot of time asking the question, okay, this is what the cosmic microwave background radiation looks like. This is what our universe looks like today. How do we get from those? Can gravity drive that structure or formation? And the short answer is it can. We weren't aware of dark matter. That allows the clustering. It drives gravity to behave or to grow things more quickly. Dark energy plays into there. All of the things that Lerner didn't like that he developed his model to correct, we found actually fit very comfortably within Big Bang cosmology. So what do you do with these claims that we've got these galaxies that don't, the Webb is finding these galaxies that don't fit within Big Bang cosmology? Well, one of the fascinating things that I have noticed over my scientific career is that astronomers are routinely arguing about things that just seem ludicrous. I mean, when I was in graduate school, we had no idea whether the universe was 10 billion years old or 20 billion years old. And you'd think that would be a pretty important thing to know, but we could not make those measurements. Some measurements said it was 10, other measurements said it was 20. And so we had these irreconcilable measurements, if you will. Well, part of the reason the Hubble Space Telescope was built was to reconcile and figure out which of those numbers is correct. And I can tell you the number comes in right around 70 to 75. And so that means the universe is, if the universe was expanding at 100, it was going to be 10 billion years old. If the universe was expanding at 50, it was going to be 20 billion years old. And it turns out it's expanding at about 70 to 75, which means the universe is 13 to 14 billion years old. And so astronomers deal with these sorts of discrepancies all the time. They actually, without those discrepancies, we wouldn't be able to push in and probe the details of those models and make them even stronger. And so what this is going to do, it doesn't rewrite Big Bang cosmology. It just says we need to go in and get a better understanding of galaxy formation. We thought at first glance in a simple model that it was going to do this way. And it's just going to be a more complicated picture. And by finding by finding these galaxies as the Webb has done, it actually provides data that allows us to discriminate amongst those more sophisticated models. Before, we just didn't have the data, so we went with the simplest one. Now the data is there, we can dig in and figure out what's the more correct model. One final comment about Lerner's model. So Lerner is saying that, hey, the James Webb found these galaxies. My model explains this better. But in my assessment, his solution is worse than the problem he's trying to solve. So he's saying, I can explain why we have these large galaxies that are more complex. But in doing so, if I adopt his model, I now no longer have an explanation for why a galaxy that is further away has a higher redshift. See, in my assessment, the distance redshift relationship is a more fundamental quantity that needs to be explained. And then you ask the question in that, how do we explain these odd galaxies? Lerner's kind of flipping that around, saying, hey, I can explain these galaxies, but I now no longer have a way of explaining large dynamics of the universe. And so did the James Webb Telescope images show that the Big Bang didn't happen? Absolutely not. I think it actually provides strong evidence. Well, it doesn't do anything to address the evidence for Big Bang cosmology. And I think what it's ultimately going to do is allow us to fill in that Big Bang model even more completely and get a better understanding of what's going on. So I'm going to stop there for a minute. I'm going to throw it back to Kirby. I know he's got some stuff, and then we'll open it up for questions and answers.
All right. So I think it's time for Q&A for Jeff. So does anybody want to start? Don Waller had asked, where can we go to see the images from the James Webb? Did you answer that question, Jeff? I think it's NASA, isn't it?
Yeah, I was going to just look that up real quick and...
Okay, well, yeah,
I'll put it in the chat for everybody.
Yeah, I think it's NASA, but I'm not sure. So Benjamin Clifton said, wow, that is brilliant. That's what I thought too. All right, Jeff, one question that I have is, so they chose the L2 Lagrange point, which is, so the Earth is between the James Webb Space Telescope and the sun. Why did they pick the L2 rather than one of the other Lagrange points? Do you know the answer to that?
That's a detail I don't know. I know you're trying to. I don't know specifically why you use the Lagrange points. It's probably because it was one of the furthest ones away. I know when you're doing infrared measurements, you want to keep your instrument cold. And most of the infrared telescopes we've launched have had a lifetime of months just because your cryogenics run out in that in that time frame. And so the farther away you are from the sun, the farther you are from the Earth, the cooler you're going to be able to keep the instrument. And so it probably minimized how much mass you had to put up, how much shielding you had to have, those sorts of things. That would be my bet.
Well, you did mention that the Earth is sometimes is basically blocking the light from the sun. So I'm wondering if that was part of it.
Actually, this just occurred to me as I was doing this. I'm gonna that's not what I wanted.
I think that's something I read, Jeff, that they picked that because the Earth kind of sits in the way of the sun, so you don't get the sun shining on the instrument.
Right. No, that's true. So you don't get the sun shining on the instrument, but this is the only configuration where your sun shield blocks out the heat from the Earth and the sun at the same time. You know, if you're at the L4 or L1 or L5 or L3, one, you're either exposed to the sun or the Earth, one of the two. And so this is a place where you have neither of those, or you can block out the radiation from both of them at the same time.
One other thing that I saw, I did a little quick search, and I saw that that the L2 is one of two Lagrange points that has an ambiguous location. So it's not very precise, but some of them are very precise. And I think that means that the ones that are very precise would tend to harbor junk, asteroids and things.
Yeah, that wouldn't surprise me. I know as I was reading, one of the things it said is that it doesn't actually sit at the L2 Lagrange point. It actually orbits around the L2.
Right. Yeah, so that makes it an ambiguous location, so that if there were junk there, it would have to be in the same orbit that it was. Yeah.
Right.
Ron Martin asked, what were the major expenditures of the 100 billion? I guess you're saying in the hundreds of billions of dollars to build and launch the James Webb Space Telescope. Do you know the answer to that one?
I don't know specifically, but I do know you just got this instrument was an instrument that they built. It was supposed to launch, I want to say back in 2015 or no,
yeah,
maybe
I think
or even
something
earlier.
like that. Yeah.
So you're paying all the people an extra decade to work on it. You're also, there's just the technical challenge of making sure this works. So with the Hubble Space Telescope, that was actually a pretty large expenditure as well. But if it didn't work, you could go get it, bring it back, fix it if you had to. Because like I said, you're 600 kilometers away instead of 1.5 million kilometers away. So this has just got to work. But from a technology perspective, the amount of mass in the mirror for equivalent amount of area is 10 times smaller for the James Webb than for the Hubble. And so, it's got beryllium mirrors on it that are gold plated. You have to do all the stuff to make sure you can actually stay cool. You got to engineer this sun shield that can unfold out in space with no help. I mean, it just the level of testing and redundancy and making sure it works and all of that goes into it is incredible. And that's just expensive. And you got to get all that mass up into space. And it took a lot longer. and it's pretty exotic materials to make all that work. So I don't know what exactly the expenditures are, but it doesn't surprise me that it's that level of cost.
And the Hubble, as I recall, I mean, I guess we probably all recall that there was a major problem, wasn't it, with the Hubble, that the major problem came up, that it was out of focus and they had to send up a team to fix it?
Right. In fact, the Hubble was precisely ground to the wrong specifications.
Yeah.
Which it was nice, because that would be better than being poorly ground to the right specifications, because you can't fix poorly ground. You can fix wrong specifications.
Right.
And so I'm pretty sure what actually ended up happening with the Hubble, I heard a fascinating discussion or talk on this once, is that there are ways you can tell whether your telescope is ground, and there are some older, more traditional ways and some newer, better technology ways. And the newer technology way in this particular instance had the Hubble mirror. There was a rod and then a detector up at the top of that. And what happened is the rod got flipped over, and that had just a slight discrepancy in the dimensions. And so that's what caused it was ground very well to the wrong specifications, which meant they could go up, put in optics to correct that. And then you lost some of your original design specs because you now no longer had the field of view or whatever. You lost a little bit, but you got essentially all of the resolution out. And so I know humans have a lot of problems, but we are really creative at figuring out how to solve problems. And some of the things we've come up with and been able to do, and then be able to build a solution that we can implement out in space is remarkable.
And yet we didn't have to do that with the James Webb, I don't think. I mean, everything seemed to work pretty much flawlessly from the start, from day one, didn't it?
It has. And I think that's part of what drives the cost up, though, is that everything is so well engineered, redundantly engineered, because you have no shot at getting it or correcting it if it's wrong. And so we tend to think you've invested that amount of money, you want it to work, but space is a pretty hostile environment. And so you get a cheap, fast, or quick, choose your two. Well, if it's got to work, and we just spent a lot of money, and you took a long time to do it because it had to work, because you couldn't do cheap or cheap, fast, and quick. No, it's not cheap, fast, and quick. It's cheap, fast, and quality. The quality had to be really high, so we spent a long time and a lot of money to make sure it worked. So
I see that Cynthia Chung, our NASA expert, has told us that to get Webb images, go to webbtelescope.org. Also see web.nasa.gov. So you can see those in the chat yourself. So and Lothar, let's see, Kirk, you've had your hand up. Not
really. That's my emoji's hand. That's not my hand.
All right. But Lothar has a question.
Yeah, I do have a question. A while ago, my wife sent me an article. I don't really remember the details, but what I do remember is that scientists were shocked that Hubble was wrong in the distance, the age of the universe being 13.8 billion years old. And is that still correct, or is that misleading?
So there are two ways we have. So a little bit of background here. So I mentioned this discrepancy back in the 1980s and 90s, where one technique of measuring the expansion of the universe gave an age of 10 billion years. One gave it at 20 billion years. That's because measuring the expansion gave two different answers. Well, we've narrowed down that answer, and it's somewhere in the 7, instead of being 50 or 100, it's somewhere in the 70 range. But as we've now narrowed in on that range, you can measure the age of the universe with the cosmic microwave background radiation. You can measure it with the expansion of the universe, And there's a discrepancy of 1 billion years when you do that. And I'm forgetting off the top of my head which one's which. I think the cosmic microwave background radiation measurements give it at 13.8 billion years, and the expansion history measurements give it at 12. You're right at 1 billion years less than that. And so that's an ongoing discussion in the scientific community. Largely why it's a discussion now and not earlier is that we didn't have the resolution to get in and say we could tell those were meaningfully different. We had, the error bars were large enough to include all that earlier. Now we've got sufficiently detailed precision in our CMBR measurements and sufficiently detailed measurements in our Hubble expansion measurements to know they're not saying the same thing. And the question is why? What are we missing? What do we need to what do we need to do to understand that? And so it is an ongoing discussion that exists in the astronomy community today.
So was there a value that the James Webb gave?
The James Webb doesn't really have any way to weigh in on this. What it might be able to do is add some more distant points because it can see further. But the challenge you have is that you don't have anything out at those distances where you can get a good distance measurement. So you can measure the redshift, but in order to extract an age, you need to get not only a redshift, but also a distance. And so Webb is just assuming the distance redshift relationship rather than measuring it. So that's not something that the Webb is designed to do. It may add a little bit of data, but it's not going to weigh in on that question.
I see. Because I think the article indicated that the Hubble may be incorrect.
Well, so there is something, we're incorrect something. And what I notice about those articles is that depending on who's writing the article, which one's wrong or which one's right has a little bit of, my guess is whoever was writing that article tended to put more credence into the cosmic microwave background radiation measurements. And I think there's good reason to do that, but they're going to likely think that the other one's off. Those who work in the distance redshift relationship are probably going to question whether the CMBR way is the correct way to do it. But regardless of which one's right or which one's wrong, and my guess is if past history is the case, we're going to end up somewhere in the middle with those because we're going to find errors that we didn't know were included in those calculations. Is that this now provides us, again, some data that allows us to refine our models and put more detail and understanding into the models, where before we just didn't have any way of discriminating between the models that might have given 14 billion years, models that might have given 13. We didn't have any way of discriminating between those. Now we've got techniques that allow us, or this will drive us to an understanding that will allow us to maybe discriminate between those types of models and get a better understanding.
Okay, thank you.
Ron Martin asks for more clarification on the cosmic radiation picture. You showed the blue and the yellow patterns, and he asked, what is the significance of the near uniformity in the cosmic background radiation?
Yeah, so I'll just throw that back up there real quick just to make sure. I assume this was the image we were talking about there. And
I assume so. Yeah, Ron's nodding his head.
Okay, yeah. So this is the map of the cosmic microwave background radiation. And for a little bit of orientation, if you take the center of the Milky Way galaxy is right here. This map, it has the center of the Milky Way galaxy there. The plane of the Milky Way galaxy runs across that. What this is a measurement of is you can look at the cosmic microwave background radiation. And what you will find is that it is uniform in whatever direction you look at it. And from that uniformity, or that uniform, the way the radiation is distributed, you can get a measurement of the temperature of the universe. And that's right about 2.7 Kelvin. Now, that uniformity it's uniform to 1 part in about 1,000 because we're moving through the universe. And so if there's another, the W map and I'm drawing a blank on this. Planck satellites didn't do these measurements, or COBE and WMAP did. Planck didn't do it because it had already been measured. You can show that if you just do a map, it's very uniform. Everything's the same. But then if you subtract off the average value, you'll find that there's a bright hemisphere, or if you cut it in a line about right here, one side's brighter, one side's dimmer, or one side's hotter, one side's colder. That's because we're moving through the universe. So we can figure out how our galaxy is moving through the universe, subtract off that component, and then you end up with the plane of the galaxy gives off a lot of microwave radiation. And if you find ways to subtract that out, you're left with this. And these are the original ripples in temperature of the original background radiation. Where it's blue, it's colder. Where it's orange, it's hotter. And where it's hotter, that means more mass is concentrated. So these are going to be, or where you've got the orangish stuff, that's where matter and galaxies and clusters of galaxies are going to be clumped up today. So this is a picture of how the mass was distributed in the universe when the universe was about 400,000 years old. So that's the significance of this picture. Does that answer the question you're asking?
Yeah, that brings more clarity to the whole thing.
Okay.
I have a kind of a follow-on question. Is it possible to look at the, well, I mean, for not me, I know I couldn't do it, to look at the cosmic background radiation that you've shown here and tie it to any known points in the universe now?
I know people have worked to do that, and it's so specifically the things they're trying to do is say, all right, we know where galaxies and clusters of galaxies and superclusters of galaxies. So even the smallest points on here are, they're clusters and superclusters of galaxies. So you're not going to say, oh, that's the blob that becomes the Milky Way. You're just not going to find that. But people have tried to do that, and you do find good correlation between where there's orange stuff, you find more matter. Where there's blue stuff, you find less matter. So they've been able to make those sorts of correlations.
Okay. I think we had a few other questions here. Let's see if I can get the chats here. Benjamin Clifton says, in the false color rendering of the infrared data from Webb, is redshift also compensated for, especially for images with both near and far objects? I'm not sure I understand the question, but if you do, go for it.
So what they're going to do is they're going to take and say, all right, if visible is from 400 nanometers, which is blue, to 700 nanometers, which is red, now you're going to have, I think, the high end of, or the shortest wavelengths that Webb deals with are right around 700 nanometers. And it's going to go down to, I think it's 1500 nanometer, or not 50, 1500 nanometers. So what it's going to do is it's just going to map those those wavelengths into the visible range. So that's where you get the false color part. Redshift compensated, that's not typically something. You're not going to do that object by object. You're going to measure the redshifts to see what, again, that allows you to get, by measuring the redshift, you're going to be able to figure out how far away something is. That will give you information. They're not going to correct it for the redshift, but by knowing where the wavelengths should be and where we expect them to be, that's how you find a redshift. So you got to have something that like a hydrogen line or a water line or a carbon dioxide line, something like that. You know where it's supposed to be because we can measure it in the lab. You know where we measure it in our spectra, and that allows you to determine the redshift and figure out how far away something is. So you're not going to compensate for it in the maps you make. You're going to make the maps in the false color, and then from that, you're going to be able to extract the redshift so that you can tell how far away something is.
I see a question that was directed to me, but I know that I don't know the answer to the question, so well, actually, I think I might know the answer to the question, but I'm going to ask this question of Jeff to clarify it, because I kind of had the same question. But I think Jeff kind of explained it. In the deep field image, he says, I saw some streaking arcs that appeared to be around the center of the image. He says, was that due to the 12.5-hour exposure and movement of the James Webb Space Telescope, similar to an Earth-based telescope taking a long exposure toward the North Star? And I think you talked about the lensing of that was coming from lensing. Yeah, that's the one, I think.
Yeah, so if you look at here, I mean, you can see again, you can see very clearly that's a star, that's a star, that's a star. You know, I mean, you got bunches of stars sitting in there. But then you've got, you know, here's a, you know, a galaxy, various galaxies of various shapes. And then you've got these things here that look like they're streaking, like it's almost like you took the exposure and something moved while you're doing it. But it turns out the whole reason they looked at this particular object is there's a bunch of mass in this object. So more distant galaxies, as their light comes by, is going to be gravitationally lensed. And that's what you're seeing. So that's going to be a gravitationally lensed galaxy. You know, let's just say this is one of the galaxies in the cluster that we're looking at. It's going to be out at, let's say it's light's been traveling to us for 3 billion years. Well, now you've got all of these kind of reddish streaks where stuff's being lensed. Those galaxies are going to be much more distant, but because of the mass in this cluster that's, you know, the 3 billion light years away, it's going to allow you to see, magnify and lens the stuff that's behind it so that you can see it. So this galaxy may be light's been traveling for 3 billion years. These are probably going to be 4, 5, 6, or 7. But it's actually further than that. I don't know exactly what they are. I know some of these lensed objects are the ones that they see the galaxies that were formed 400 million years after the Big Bang. So all of those streaks are not due to motion through the field of view. Those are gravitational lens that tell you, or from galaxies that are even farther away in the background.
Which isn't that a function of general relativity?
Yes.
The lensing is a function of, okay, sorry, go ahead.
Yeah, general relativity. So if you were to have something directly in between us and a more distant object, the light as it passes by, normally it would pass by, and if it were going a little bit at an angle to us, it'd just pass by and go right by us and we'd never see it. The mass of that object will cause that light to be bent and focused around, and it actually works like a lens. It will focus that light, so you get more light than what you would have seen from a more distant object. And so if it's just lined up in a geometry, you're going to see a circle. The fact that the mass is spread throughout this cluster and that you're a little bit off axis, that's why you get these arcs. Those are gravitational lensed arcs that you see. And so that's just a telltale signature that you're seeing gravitational lensing there.
I was personally expecting to be able to see what it was that was causing the lensing, but I can't see anything that in there. Is this dark matter that's actually causing the lensing, or why can't we figure out? Why can't I figure out what's causing the lensing of each one of those?
Because you're seeing the cluster, I mean, my guess is I'm almost positive that galaxy is going to be in the cluster. There are a couple, these ones that all kind of look about the same. I'm betting they're all in the cluster. In a cluster of galaxies, though, most of the mass is actually in hot X-ray gas that's in between all of the cluster, or the galaxies in the cluster. So the galaxies are a relatively small fraction of the mass that's in the cluster, and on top of even of the normal matter. And then you add on top of that the dark matter, and that's all distributed in there. So you're right, it looks like, hey, there ought to be an object where these are all getting lensed around, but the way galaxy clusters look, they're going to be a few bright galaxies that you can see, but most of the mass you're only going to see if you look out with an X-ray telescope.
Okay.
Because that's where you see the hot X-ray gas.
All right. Any other questions? Go back to our, let's see. Ken, that was a good question. I didn't mean to put you on the spot, but any other questions?
I do have to say I'm with you, Kirby. It looks like Kirk's wanting to ask a question all the time. So
Come on, Kirk, ask a question. Okay, well, I guess there's no point in keeping everybody here if, so Sabina has a question.
all right.
Yes. Jeff, thank you so much. It was awesome and inspiring on various levels. I am wondering, is it by any chance possible to get a copy of your slides and or the presentation?
Um,
I mean, I'm
I-
sorry,
that-
I should actually ask Kirby probably because you're recording, right?
I am
Yeah.
recording it. Yeah. So we'll hopefully we'll be able to I'll put it up on YouTube if it looks okay,
Is it okay with
if I
Jeff?
didn't mess things up too bad.
Yeah, my only hesitation in saying yes is that I took a whole bunch of images from the website and haven't gone through and worried about putting all the attributions and credits on there. And so that's my hesitation in having it distributed. I do think, given that it was recorded, going back and watching the recording and just, acknowledging that all of those, virtually every one of those was from the webtelescope.org or a related site like that.
Mhm.
And so, just recognizing that attribution. But quite honestly, you can go find most of those pictures I don't look very hard on the website, and they just show up and they give great descriptions below of what all of them are.
I
Right,
will
actually-
say that YouTube is very good at reviewing videos that I put on to see if there's any trademark or copyright issues, and they'll slap me if I do. So
I suspect
I
the
don't
web
think
images
I don't
are
think
all-
they're for
I
NASA.
think
I
they're all
don't think there's
public.
going to be any problems. But
Yeah.
And Jeff, it's actually, you're right, I can get the images, but it is what you said that made them, even more fascinating. And thank you for being with us.
Yeah, then having the YouTube or the recording would be better there too, because then you can go back and listen. So
Yeah. Yep.
one new message.
Yeah.
Okay, so Ron Martin asks, in the chart of the wavelengths with telescopes along the continuum, what is the I don't see the rest of the question.
Oh, sorry.
Sorry.
Sorry, I remember looking at his question.
Go ahead, Ron, and can you unmute yourself and
Well,
finish the question?
I see the abbreviations of the telescopes, but what are their names and how long have they been operational?
So the VLA has been operational for decades. I know even when I was in graduate and undergraduate, it was operating. So that's at least back in the 70s is when that one was started working. I mean, I know it's been upgraded and everything since then, but that's at least 60s or 70s back, and that's radio wavelengths.
What does VLA signify?
Very large array.
Where is that, in Arizona?
It's
on the
either
East Coast.
Arizona or New Mexico. I can't remember which.
Okay.
WMAP operated from early 2000s, like 2001-ish, through about 2000. Let's say it was 9 years. So it's let's say 2001 to 2011. It's still up in space, I think, but it's just no longer operational. James Webb has been up for less than a year. Hubble. Oh, good grief. When was it launched? I know it was supposed to have been launched right before the Challenger disaster and was launched shortly after that. So it's been going on 2 decades now. Rossi, so this is the Rossi X-ray telescope experiment. I'm not sure that one's still running, because typically when you're doing X-rays, I forget whether this is one where it was where you're detecting the particle or whether you're focusing the mirrors. This instrument would have largely been superseded by the Chandra X-ray telescope, which was launched in the 1990s, late 1990s. Swift was a gamma ray instrument that was launched in the 90s as well. It's still up, but it was succeeded by Oh, good grief. I'm drawing a blank on the name. The Fermi. Nuts. What's the name of it? This is one that it launched right about the time I finished graduate school. It's called Fermi is the name of the instrument. And it's there were 4 great instruments. There was Fermi, there was Chandra, there was a Hubble Space Telescope, and there was an infrared satellite that was launched. And those were the 4 great observatories that were launched. I think it was IRAS was the infrared telescope. And Hubble's still running. IRAS infrared is no longer good because its cryogenics no longer work. Chandra, I still believe, is still taking data. In fact, a lot of the utility of the James Webb is being able to do multi-wavelength observations correlating the Chandra observations with the Webb observations. And then Fermi, it's still operating and will be for quite some time. It was an instrument that doesn't need to be like have an expendable fuel in it or anything like that. So I'm pretty sure it's still up and running and still finding lots of interesting stuff.
Any other questions before we let Jeff go? Are there any more questions here? Actually, I am going to ask one more, Jeff, and that is, I didn't see in anything that you were showing how the dark energy shows up. I was basically looking at the Hubble curve, and and I think you had a couple of other curves that you were showing for how redshift works. But my understanding is that the dark energy idea came up and shows that it's actually the velocity is expanding faster than linearly. Or do I misunderstand?
No, that is basically the idea. I'll go back to, this is the slide I was showing.
Yeah.
So what you've got here is the redshift distance relationship. So redshifts on the x-axis, distance is on the y-axis. And what you find is you got this nice linear relationship. But as you get farther and farther away, what you notice here is that these different curves, and you can see the dashed one is where all of the energy density of the universe is in mass. And so that's going to be this dashed curve down here is what you would expect, because the universe is going to slow down over time. And if you make this plot, it's going to, it's going to look like that. Here you've got where there's only mass, but we fall short of the critical density because there's no dark energy. And that's going to be this line down here. And you say, well, that might fit it. But what's a far better fit is if you've got a universe where mass is about 30% of what's there and dark energy is the other 70%. That fits all those data points a lot better. And so it's not so much that you see things starting to fly off. Well, that is what ends up happening here, because if it's decelerating, you're going to drop off as you come up here. If it's accelerating, it's going to get larger, and that's what you see is that it's getting larger than either of the, or than that. And so it doesn't look particularly elegant or particularly compelling there, but when you do the analysis, the omega mass 0.3, omega lambda 0.7 is clearly the better fit.
I see. Okay. I guess the other surprising thing to me is to see how much variation there is in the distant objects. It looks like there's very big error bars, as well as to the fact that some of them are way above the line, some of them are way below the line. So it's very interesting.
That's a lot of what astronomy data looks like. I mean, a lot of it is, can you build enough statistics to make a case? So any individual event or object is not going to answer the question. It's going to be a statistical assessment of it, because it's really hard to pin down the systematics on all of those down to where your error bars on any individual measurement are that precise.
Okay, last chance. Anybody want to step in with a last question? Go ahead, Ben.
Yeah, one last question. Jeff, and thank you, Jeff. This was great. Do you foresee that the Webb will bring any new, let me just call them nails in the coffin for young Earth creationism?
So I'm just trying to think, there's part of me that says, if the nails we have aren't enough, Webb's not going to bring anything new. But I'm trying to think what the Webb might bring in there. One place I think where the Webb could bring in something, and the hard part is that it's going to be a little bit interpretation laden, or it's not going to just pop off. There's analysis to get to it. Is that what Hubble did in looking at the Eagle Nebula was see there are these big giant gas clouds. They can see the outsides of the clouds, but they don't see what's going on inside. And you get down and you zoom in and you find that there are these blobs and cluster stuff. And it's like, okay, the argument was that's where stars are forming. Now you've got Webb, which looks through that dust and actually sees the stars that are forming there. And so it will remove one of the objections of, oh, we don't see stars forming, how can this all be going on? Because we actually see more of that process going on. And it kind of removes a little bit of the veil that allows us to see this very transient phase of a star's life. And so I think that's one area where I see Webb could actually provide us a lot of data and a lot of insight into what's going on, just because we've never been able to see the place where a star starts to burn or turns on is a pretty rapid amount of time, and it's shrouded in this big cloud. Well, we may be able to penetrate the cloud and get some statistics on what's going on in there. And so I think that would be one area where that would be another big nail in my assessment.
Okay, thanks, Jeff. And if there are no further questions, since I forgot to open this meeting with a word of prayer, let me close this meeting with a word of prayer. Let's all pray. Gracious Lord God, thank you so much for the opportunity that we have to watch, to witness these wonderful new instruments that are being produced every day, that we can see farther and farther and deeper into your amazing universe. We just marvel at what we see, and it's just incredible. And we just thank you, Lord, that you have given us the opportunity to live in this time when we can actually see all these things. And we just we praise you, Lord, and we just thank you. And we ask that you would watch over us now as we go on to the rest of our lives. And we just praise and worship you. In Jesus' name we pray. Thank you, Lord. And thank you, Jeff, for a marvelous presentation. I think we're all very happy about it.
Well, thank you. Like I said, I had a lot of fun going out and doing the research for this one. It's
Okay,
it's
great.
a pretty remarkable instrument. So
yeah. Okay, I'm going to stop recording at this point.